Welcome again to my journey into discovering what centers are. Grab something nice to drink, take a seat, take a break from your day, and let's continue. So the first video I talked about measuring center in terms of the square distance metric. And this gave us the mean. The second time I talked about the absolute metric, which gave us the median. And this time I'm going to talk about the discrete metric, which is the metric that distinguishes between if things are exactly the same or not. And here it's the orange crosses. You can see this metric says it's 0 if x is exactly t. It's 0 if you're exactly the same thing, and 1 otherwise. So everyone who's not the same as me is distance 1 from me. It's quite a neat idea, and maybe an extreme case in some sense. So with discrete, I'm going to write 0 if x equals c, 1 else. What does this give us? Well, have a guess, and we'll do it. So my proof here is going to only work on discrete random variables. So x takes on a discrete range of things, and we don't deal with probability densities. I'm not really sure how to talk about integrals in that way. I think there's a limit approach that we could use more generally, but if you know more about this, let me know. So for the discrete case, the expected value of x is equal to the sum of x times the probability that big X is equal to little x. This is weighted center of mass. And for the case of the discrete metric, we're interested in the expected value of 0 if x equals c, 1 otherwise. And so we could replace the x here with this by a theorem about expectations. Write px as a shorthand. So here you could see that everything in this sum is going to disappear. No, everything is going to stay here, except for the single case when x is equal to c. So you might think of this as we have our entire situation, the entire sum of probabilities, except we'd gotten rid of the probability that x is equal to c. And since the entire sum of probabilities is 1, that means our expected spread is going to be 1 minus the probability that x is equal to c. So this is going to be minimized when this expression is maximized, when c is the highest probability value x could take. In other words, c is the mode. This is cool. It's the mean, median, and mode. The three musketeers, they've been reunited under these 3 different metrics. And now we might ask, do we have an extended family for them? And the answer is yes, and the answer is, I don't know what that's about. It's about metric spaces. Apparently there's this family of metrics from what are called LP spaces. And the metrics are of this form, that the distance of x to c is equal to the sum of, x to the p plus c to the p to the power of 1 over p. So p could take on a bunch of stuff. And if you compare these guys, these are actually all special cases. The ones I talked about are all special cases of this family of metrics. for the square distance, this is when p is equal to 2. No, it's not when p is equal to 2. What's going on? Oh no, I forgot. I'll come back to this when I figure it out. But I hope you enjoyed that. I think this is one step closer to understanding what expected values are. And it gives us this whole family of ways of measuring centers. And for the median, in higher dimensions, it generalizes to something called the geometric median, which I find a really fascinating concept. You might want to check that out. I hope you have a nice day, wonderful day.